All right, let's continue with our next module here. We're going to be talking about reactance, impedance, resonance, and active components in this section. So let's talk about reactance. Reactance is the resistance to the flow of current caused by capacitance or inductance. It's denoted by the letter X and is measured in ohms, like resistance. Capacitive reactance, which is the opposition to AC current flow from the stored energy in the capacitor, is denoted by XC. Capacitors behave differently with AC and DC current. With DC, when voltage is instantly applied, capacitor looks like a short circuit. After charging, it looks like an open circuit. This is how it blocks DC signals. However, AC behavior depends upon voltage frequency. Here you can see a graph. If you have a capacitor, as soon as you apply voltage, it's a short circuit, and the voltage rises up to the applied voltage over a specific amount of time. And when you remove the voltage from the capacitor, then it slowly decays down to 0 volts again. So when a circuit containing a capacitor is first energized, the voltage across the capacitor is 0, and the current's very large. As time passes, the voltage across the capacitor increases, and the current drops toward 0. As the frequency of the applied signal increases, the reactive capacitance decreases, and vice versa. What is the reactance of a 1 nanofarad capacitor at 2 megahertz? Well, first we have to convert megahertz to hertz and nanofarads to farads. 2 megahertz is 2 times 10 to the 6 hertz. 1 nanofarad is 1 times 10 to the minus 9 farads. So the equation of capacitive reactance is 1 over 2 pi the frequency times capacitance. So in this case, it's equal 1 over 2 times 3.4 times 2 times 10 to the 6 times 1 times 10 to the minus 9, which comes out to be 79.6 ohms. So the capacitive reactance of a 1 nanofarad capacitor at 2 megahertz is 79.6 ohms. Inductive reactance is the opposition to AC current flow from the stored energy in an inductor and is denoted by XL. Behavior with frequency is described as below. XL is equal to 2 pi times the frequency times the inductance in henries. As the frequency F of the applied signal increases, XL increases, and vice versa. When a circuit containing an inductor is first energized, the initial current is 0, and the full applied voltage appears across the inductor. As time passes, the voltage drops down towards 0, as shown in this figure, and the current increases, as shown in B. What is the reactance of a 10 microhenry inductor at 5 megahertz? First, we convert microhenries to henries and megahertz to hertz. That way, everything has the same base units. So 5 megahertz is 5 times 10 to the 6 hertz. 10 microhenries is 1 times 10 to the minus 5 henries. And from our equation, the inductive reactance is 2 pi times the frequency times L. So in this case, it's 2 times 3.14 times 5 times 10 to the 6 times 1 times 10 to the minus 5, or about 314 ohms. So the reactance of a 10 microhenry inductor at 5 megahertz is 314 ohms. Parasitic inductance is unwanted. A parasitic inductance is an unwanted characteristic that results from the component's physical construction. The coils in a wire-wound resistor, for example, create parasitic inductance. Wire leads of components add inductance, parasitic inductance. And in inductors, each pair of turns creates parasitic capacitance in series with the inductance, often significant enough to disrupt the circuit's operation or affect tuning in the radios. Some capacitors made of thin foils are rolled up. The rolled up construction creates parasitic inductance. It's very high in electrolytic capacitor. This limits their use to relatively low frequencies. Tantalum and ceramic capacitors have little parasitic inductance and can be used up to microwave frequencies. What is reactance? Is it the opposition of the flow of direct current caused by resistance? Nope. It's the opposition of the flow of alternating current caused by capacitive or inductance. So that's what reactance is. Which of the following causes opposition to the flow of alternating current in an inductor? It's going to be reactance. Which of the following causes opposition to the flow of alternating current in a capacitor? And it's reactance. How does an inductor react to AC? As the frequency of the applied AC increases, the reactance decreases, or does it increase? All right, so the frequency increases as the applied AC increases, which is D. As the frequency goes up, inductance goes up, the reactance. How does a capacitor react to AC? Well, it's the opposite. So as the frequency goes up, the reactance decreases in a capacitor. So it'd be A. What unit is used to measure reactance? Okay, be the ohm. Why should wire-wound resistors not be used in RF circuits? Let's see, the resistance inductance could make circuit performance unpredictable. The internal resistance capacitance would detune the circuit. So I think it's going to be D. Nope. The resistance inductance could make performance unpredictable because there's parasitic reactance in there. Okay. Impedance is the opposition to current flow in an AC circuit caused by resistance, reactance, or any combination of the two. It's also, impedance is denoted by the letter Z. It's measured in ohms. So remember, impedance is the opposition to current flow in an AC circuit caused by resistance, reactive, or any combination of the two. Okay, like resistance, it's the ratio of voltage to current. It's the inverse of impedance is admittance. So resonance indicates a match between the frequency at which a circuit or antenna naturally responds to the frequency of an applied signal. Resonance occurs when capacitance reactance is equal to inductive reactance. So when those two are equal, then you're going to have resonance. In a resonance series circuit, reactance of L and C cancel, making a short circuit, leaving only the resistance as the circuit's impedance. Resonance is used in filters and tuned circuits to pass or reject specific frequencies. So resonance is a very important piece of amateur radio, used a lot in our RF circuits. In a resonance series circuit, the reactance of L and the reactance of C cancel, making a short circuit. This leaves only the resistance as the circuit's impedance. Self-resonance. Resonance can occur when a component's expected reactance equals the reactance of its parasitic reactance, called self-resonance. Self-resonance results in a component that appears to be short or open circuit at the self-resonant frequency. Above this frequency, the component's reactance switches type, making an inductor capacitive and a capacitor inductive. So that's above the self-resonance frequency of the device. Impedance transformer is a transformer that can change the combination of voltage and current while transferring energy. The transformer also changes impedance between the primary and the secondary circuits by changing the ratio of voltage and current between the primary and secondary circuits. The turns ratio controls the transformation in the same ways as the ratio of gear teeth in a mechanical transmission. So, impedance transformers, this is real similar to the voltage transformer we just saw, except we've got impedance now. What is the primary impedance of a 200 ohm load is connected to the secondary of a transformer with the 5:1 secondary to primary turns ratio. Well, using our equation, fill in our numbers, it's 200 divided by 1/5, which is about 8 ohms. So if I've got a 200 ohm load, if I got 200 ohm impedance on one side of a transformer and a 5:1 winding ratio, it will transform that impedance to 8 ohms. Okay, what turns ratio is required to change a 600 ohm impedance into a 50 ohm impedance? Well, it's going to be the square root of the impedance ratio. 600 divided by 50, square root of 12, 3.46. So if I had a 600 ohm impedance on one side of my transformer and I needed to get to 50 ohms, I'd have to have a turns ratio of 3.46 in my windings. Note that the impedance to be changed, in this case 600 ohms, can be connected to the primary or secondary, but turns ratios are always stated with the larger number first. 3.46 to 1, not 1.3.46. Because remember, a transformer, you can hook up both directions, but it's always stated with the turns ratio of the primary first. An energy source's ability to deliver power to a load is limited by its internal impedance. Amateur transmitting equipment is designed so that the internal impedance of its output circuits is 50 ohms. If the difference between the antenna system impedance and the transmitter output impedance is greater enough, the transmitter may reduce output power to avoid damage. So what you need to do is put in an impedance matching circuit. This is the case where you've got an antenna that's other than 50 ohms. Most impedance matching circuits are LC circuits, inductors and capacitors. They are called pi or T networks based on how they're configured. On the left is the pi network. You notice it's a inductor with 2 capacitors, and a T network is 2 capacitors with 1 inductor. Impedance matching can also be performed by special links and connections of a transmission line. Okay, what happens when an inductive and capacitive reactance are equal in a series circuit? Resistance means the impedance is very low, impedance is equal to the resonance. I think it's going to be C. The resonance causes impedance to be very low, so the two cancel each other out and you only have the resistance value left, the real resistance. What is the term of the inverse of impedance? Admittance. What is impedance? It's the ratio of voltage to current. Remember, similar to E equals IR. Which of the following devices can be used for impedance matching at radio frequencies? A transformer, a pi network, length of transmission line, all the choices. I think it's all of these. Remember we talked about a transformer, a pi network, a transmission line, all of these can be used to transformer match. What letter is used to represent reactance? X. What occurs in an LC circuit at resonance? Current voltage are equal? Nope. Circuit? Nope. The inductance, reactance, and capacitance cancel each other. D. What transformer turns ratio matches an antenna's 600 ohm feed point to impedance to a 50 ohm coaxial cable? It's about a 3.5 to 1. A. What happens when an inductor is operated above its self-resonant frequency? It becomes capacitive. Remember, inductor above its self-resonant, inductor becomes capacitive, and a capacitor becomes inductive above its self-resonant frequency. What is one reason to use an impedance transformer at a transmitter output? Present desired, reduce to minimize, to present the desired impedance of the transformer feed line. B. Okay, talk about some semiconductor components. The most common active components are made of semiconductors. Most are made of silicon or germanium. Electrical properties can be controlled by addition of small amounts of dopants or impurities such as indium and phosphorus. If the impurity creates an excess of electrons, the result is an N-type material. And the opposite, deficiency of electrons, is P-type. So those are the two types of semiconductor materials that we commonly use. Where N-type and P-type are in contact, where those two come together, it's called a P-N junction. Okay, here's a diode. Semiconductor junction, this is a diode that uses a P-type material, and an N-type. P has excess electrons, N has deficient electrons. When those two come together in a boundary, it's called a junction. And let's see, current flows when positive voltage is applied from the P-type to N-type material. That's called forward bias. And if I hook the power up backwards, it's not going to flow. So current flows when positive voltage is applied from P to N forward bias. Voltage applied in the opposite direction is called reverse bias. It pulls electrons away from the junction so no current can flow across the junction. Voltage required to force electrons across through the junction is called forward voltage or junction threshold voltage. For silicon diodes, the forward voltage is 0.7 volts. For germanium diodes, it's 0.3 volts. There's different types of diodes. There's light emitting diodes called LED, laser diodes, avalanche, Zener, Schottky. There's a bunch, and they're all diodes, and they have different applications and different properties, and can be used for different types of things in your electrical circuit. Diodes are rated by their peak inverse voltage. That's the maximum voltage they can stand before breaking down negatively. They're specified with their forward voltage, how much voltage it takes to turn the voltage on to get forward current flow. Exceeding a diode's rating will destroy the diode's internal structure. Junction capacitance, when reverse biased, layers of the P and N type material act like capacitors. The larger the C, the longer it takes to switch it to conducting forward current. So if you want something that switches fast, like a transmit-receive diode, or you want something that's got lower capacitance in the junction. If we add a third layer of semiconductor material, you get a transistor. This is a bipolar transistor. You notice you've got two P-type materials with an N between them. That's called a PNP transistor. And if you have N-type materials on the end with the P-type in the middle, it's called an NPN transistor. These are the two basic types of bipolar transistors. They've got to have power on them to function. There's three electrodes. There's the collector, the base, and the emitter. And they're controlled by the current flow between the base and the emitter. Very little base emitter current is required for collector emitter current to flow. The control of large current by smaller current is called amplification. The ratio of collector emitter current to base emitter current is called current gain. Current gain for DC signals is abbreviated with beta. Current gain for AC signals is HFE. Field effect transistors has three electrodes, a diode, a source, and a gate. Instead of controlling drain source current with gate source current, the voltage between gate and source is used. Instead of current gain, FET has transconductance, which is the ratio of source drain current to gate voltage. So bipolar transistor uses current to control flow. Field effect transistor uses voltage. MOSFETs, which stands for metal oxide semiconductor FETs, use oxide layer to insulate the gate. So when you look at the figure on the right here, here's an N channel. It's got a P material with N and a P in the middle, and then the opposite is a P channel FET, which has an N channel substrate. FETs are very sensitive. They require only small amounts of voltage to control the source drain current. High amplification makes them ideal for use as switches, both voltage and current. With enough voltage, transistors can be driven into saturation, where further increases in input results in no change in output. High enough input signals can reduce output current to zero, which is called cutoff. Saturation and cutoff conditions are excellent representations of digital on-off signals in logical circuits. So what is the approximate junction threshold of a germanium diode? And it's about 0.3 volts. And the forward threshold voltage of a silicon junction diode is 0.7 volts. And what are the operating points of a bipolar transistor used as a switch? That would be saturation and cutoff. Which of the following describes a MOSFET construction? Let's see, the gate is surrounded by... The gate is separated from the channel by a thin insulating layer. Okay, talk about vacuum tubes. Vacuum tubes have at least 3 electrodes called elements. The 3 basic parts are the source of electrons, the electrode to collect the electrons, and an intervening electrodes that control the flow or the travel from source to collector. So you've got a source, a place to collect them, and something to control them, the 3 parts of a vacuum tube. Compared to transistors, they're most like the FET. Tubes operate at high hazardous voltage, 2,000 to 3,000 volts, so always exercise caution when working around vacuum tubes. A filament or heater heats the cathode. It's causing it to emit electrons inside the tube. The cathode is the source of electrons, and the control grid, which is the grid closest to the cathode, is used to regulate the electron travel between cathode and plate. The screen grid, which is the electrode that reduces grid to plate capacitance. Suppressor grid prevents electrons from traveling from plate to control or screen grid. And the plate collects electrons, and that's called plate current. Which element of a vacuum tube regulates the flow of electrons between cathode and plate? That'd be the control grid. What is the primary purpose of a screen grid in a vacuum tube? To reduce grid to plate capacitance. Now we'll talk a little bit about analog IC circuits. An IC is an electronic circuit formed on a small piece of semiconducting material, performing the same function as a larger circuit made from discrete chips. ICs can operate over a continuous range of voltages and currents. They're used for amplification, filtering, measurement, voltage regulation, and power control. Most common analog ICs, operational amplifier, and linear voltage regulators. Op amps are used for DC and audio circuits. They're an inexpensive source of gain. Linear voltage regulators maintain power supply output at constant voltages over a wide range of currents. So ICs are used in just about everything that we have today. All these modern radios we have lots of chips in them. The popular 741 op amp symbol, here's what an op amp symbol looks like. Shown in a package, what's called a dual inline package, or a DIP. And it's got connections 1 through 8. You can see the schematic, how it's pinned out. And then there's a TO220 package, which is real common for a voltage regulator. And that's what they look like. Digital integrated circuits operate with discrete values of voltage and current, representing the binary numbers between values of 0 and 1. That is representing on and off. Digital ICs are used for performing computations or controlling functions. The most popular logic family is CMOS, which stands for complementary metal oxide semiconductor technology, known for high speed and low power consumption. And here's a chart that shows the logic family characteristics of the different types of families: TTL, CMOS, and CMOS, the 4000 series. You can see the operating frequency ranges, power consumption, and the supply voltage. The basic building block of digital circuits are called gates that perform inversion, that is, changing 1 to a 0 or vice versa, in the OR and AND functions. The most common gates in use are the inverter, NAND, and NOR. For more complex functions, such as microprocessors and signal processors, they're constructed from combinations of these functions. So all the inverter, NAND, and NOR are the basic building blocks for all the big microprocessors that we have. It's just a whole bunch of combinations of those gates. Circuits that use gates to combine binary inputs to generate a binary output, or combination of binary outputs, are called combinational logic. And here's some schematics for some basic digital functions with the logic equations and truth tables that describe their operations. So if you look, a logic symbol for an AND gate, A and B, and C. So C, the output, if the input, if the inputs are the same, if any input 0, the output 0. If the inputs are ones, then the output 1. So they both have to be the same to have an output of 1. An OR gate takes the two inputs and ORs them together. So if I have any input has a 1 on it, the output's going to have a 1. A 2-input AND gate, either A and B are off, the gate is off. Both have to be on for the gate to be on. For a 2-input OR gate, either A or B are on, the gate is on. Both have to be off for the gate to be off. Can you think of examples where this might be used? Maybe a gumball machine. You need to insert a coin and press a button to dispense. So you got to do this and that, then something happens. Or an intrusive detection. Alarm sounds for intrusion or the front door or bedroom window. So you either have this window, or either this alarm or this alarm. That's an OR function. Schematic symbols for the basic digital functions with the logic equations and truth tables are described in their operation. So here's an inverter. Whatever the input is, it converts it to the opposite. So a 0 becomes a 1, 1 becomes a 0. In the 2-input NAND gate, it's the two inputs. It's the invert of the AND gate. So if I want the output to be a 1, any of the inputs have to be, any of the 1 inputs have to be 0. If I want the output to be a 0, both inputs have to be a 1. So here's a NOR gate, and again, it's the opposite of the OR gate. It takes the output of the OR gate and inverts it. So if I have any input that's a 1, the output's a 0. If both inputs are 0, the output's a 1. And here's a flip-flop. The flip-flop is used to store the next condition. So if I have an input, if my inputs are 1 and 1, and I get a clock, the output's 1 and 1. If the input's 1 and 1 goes to the next state, the output's going to be a 0. So sequential logic circuits combine binary signals in a way that depends on time and on the sequence of inputs to the circuits. Basic building blocks for sequential logic is the flip-flop. It responds to a clock signal that causes its output to change based on input. The two outputs, Q and Q bar, are always in opposite states. Connecting the flip-flops together to one flip-flop's output feeds the next one's input, which creates two important circuits called a counter and a shift register. In counter logic, the outputs of the chain of flip-flops make up a binary number or state representing the number of clock signals that have been occurred. Each flip-flop stores 1 bit of the total count. Highest number of counter can represent the highest number a counter can represent is 2 to the n, where n is the number of flip-flops that make up the counter. A 3-bit counter, which has 3 flip-flops, can count 2 to the 3 or 8 states. A 4-bit can count 16 states, a 5-bit 32 states, etc. Shift registers, if you connect the array of a flip-flop slightly differently, results in a shift register. Shift register stores a sequence of 1s and 0s from its input as the flip-flop outputs. Each clock signal causes the value of the shift register's input to pass or shift to the next flip-flop in the string. Some shift register circuits can be configured to shift up and down, or forward and backward. A simple form of a digital memory. RF circuits, they're designed to function as either like low-level, high-gain amplifiers, mixers, modulators, demodulators, filters. They greatly reduce the number of discrete devices required to build a radio circuit. So you can get an RF integrated circuit that has a lot of these components already built into it. Monolithic microwave integrated circuits, MMIC, are special types of RF ICs that work through microwave frequencies, and they perform several functions. They enable construction of low-cost cell phones, GPS receivers, and those types of things. So what is meant by the term MMIC? It is a monolithic microwave integrated circuit. Which of the following is an advantage of CMOS integrated circuits compared to TTL circuits? Low power consumption. What kind of device is an integrated circuit operational amplifier? It's an analog device. Which of the following describes the function of a two-input AND gate? Okay, output is high only when both inputs are high. That would be B. How many states does a 3-bit binary counter have? So remember, you take 2 to the n. If it's 3, it's 2 to the n, so that would have to be 8. What's a shift register? Clocked array of circuits that passes that data in steps along the array. It's A. Okay, microprocessors and microcontroller ICs that are capable of performing millions of computing instructions per second. That's what a microprocessor is. Programs must be stored in memory devices so the microprocessor can read the instructions. There's volatile memory, which loses the memory when the power is removed. There's non-volatile memory, which stores the data permanently even without power. And there's random access memory, which can be read and write from or written to. Then there's read-only memory, which stores data permanently and cannot be changed. Data interfaces. Microprocessors communicate through data interfaces. There's 2 types, serial and parallel interfaces. Serial transfers 1 bit at a time in each direction. Parallel transforms multiple bits in for each operation. 1 byte is typically 8 bits. And 1 bit, there you go. Amateur equipment uses 2 types of devices to present information: visually, indicators to present information visually, either indicators or displays. Indicators present on-off information, usually by the presence or the absence of light or color. Common indicators include incandescent light bulbs and light-emitting diodes for indicators. Displays, they present text or graphics information in visual form. LEDs have largely replaced incandescent light bulbs in amateur equipment. They last longer, can be turned on off more quickly, use less power, and generate less heat. They're also available in many colors. And they're made from special types of semiconductor material that emit light when the p-n junction is forward biased. So LED, like the term says, is a diode. Liquid crystal display, probably the most common type of display, is created by sandwiching liquid crystal between glass panels. A pattern of electrodes is printed in a thin film on the front panel with a single electrode covering the rear panel. A voltage is applied to the front panel, causing the crystal to twist in a configuration that blocks light. LCDs require ambient or backlighting. The light source behind the crystal layer, since the crystal layer does not generate light on its own. Compared to LCDs, LEDs have higher contrast where there is a high ambient light on a sunny day. How's an LED biased when emitting light? It's forward biased. We're going to be talking about practical circuits, basic test equipment. All right. Yeah. Amateur radio electronic equipment requires DC power, so a power supply is required to make it run from household AC power. Most amateur radio equipment uses DC power of 13.8 volts, which is chosen to be compatible with vehicle power systems. Power supplies have 3 basic parts: the input transformer, a rectifier, and filter regulator output circuit. There's 2 types of rectifier circuits here. A half-wave rectifier converts only 1/2 of the input waveform. This creates a series of pulses of current in the load of the same frequency as the input voltage. A full-wave rectifier converts the entire input waveform 360 degrees. This is really 2 half-wave rectifiers operating on the alternate half cycles. It requires that the transformer be center tapped to provide a return path for current following the load. So if you take a look at the picture here on the right, so a half-wave rectifier, the output of a half-wave, so you got AC coming in, and the diode blocks half of the negative cycles, so you get an output that looks like this. On a full-wave rectifier, you block half of it coming one direction and half it going the other direction, and so you get the negative sine wave shows up on the top, so it conducts in the opposite direction. I get three voltages here versus 6 on this end. So I'll have less ripple. The advantage of a full wave rectifier is that the output is produced during the entire 360 degrees of the wave cycle. It's more efficient. The output from full wave rectifiers in a series of pulses at twice the frequency of the input voltage. So if my input voltage is at 60 hertz, full wave rectifier is going to have 120 hertz frequency range. And here's a full wave rectifier. You can see, let's see, this circuit adds two more diodes for a total of 4, but eliminates the need for the center tap winding. Another type of full wave rectifier, this circuit adds 2 diodes, total of 4, but eliminates the need for center tap winding. Rectifier output pulses are used, these full wave rectifiers are used in power supply filter circuits. Rectifier output pulses of DC current don't provide a stable voltage for direct use by electronics. The variation in output voltage is called ripple. Pulses must be smoothed out by a filter network, which consists of capacitors and inductors. Most common way to reduce ripple is a filter capacitor or a capacitor input filter. Older high voltage circuits may use what's called choke inductors. So power supply safety, fuses in the primary are used to protect against short circuits or excessive current loads. Bleeder resistors discharge stored energy when the supply is turned off. So when you turn off a power supply, sometimes if you have like a light on, you'll see the light stay on and it finally goes off. That's the bleeder resistor in there feeding off the voltage. Because a lot of these power supplies have a large capacitor on them to get rid of that ripple. And if you don't bleed off that charge, it will stay there for a while. So that's called a bleeder resistor does that. Working on power supplies, you need to wait for the bleeder resistor to discharge the energy, even if it's unplugged. Okay, switch mode power supplies. The AC input is first rectified and filtered. A transistor switch pulses at high frequency, usually 20 kilohertz in that range or more, to transfer energy to the filter capacitor, which smooths out the ripple. High frequency enables power supply to quickly change to current demands and means that small, lightweight inductors and capacitors can be used to filter the output. Here's a block diagram of a switching power supply. AC's first input to the rectifier, AC input is first rectified and filtered. Transistor switch then supplies current pulses to a small inductor or transformer, which transfers the energy into another filter capacitor that smooths the pulses for a steady output voltage. The high frequency of the pulses means that the supply can react quickly to changing current demands. The high frequency also means that small, lightweight inductors and capacitors can be used to smooth out the pulses and filter the output. So what is the function of a power supply bleeder resistor? Well, you remember it's there to remove the voltage. It discharges the capacitor, the filter capacitors when the power is removed. Which of the following components are used in power supply filter network? Diodes, transformers, and transducers, capacitors, and inductors. It'd have to be C. Which type of rectifier circuit uses 2 diodes and a center tap transformer? It'd be a full wave rectifier. What is characteristic of a half wave rectifier in a power supply? Only 1 diode is required. That ripple frequency is twice that of the current can be drawn. A only has 1 diode, half wave rectifier. What portion of the AC signal is converted to DC by a half wave rectifier? 180 degrees. What portion of AC cycle is converted to DC by a full wave rectifier? 360 degrees, because it's doing the full wave. What is the output waveform of an unfiltered full wave rectifier connected to a resistive load? Series of DC pulses at twice the frequency of the AC output. When you remember you have the full wave rectifier, you've got both the high and the low, so it's twice the frequency coming out. Which of the following is characteristic of a switch mode power supply as compared to a linear power supply? High output, let's see, viewer circuits, high frequency. It's going to be high frequency operation, use of smaller components. Okay, now we're going to talk about batteries and chargers. There's two types of batteries, primary and secondary. Primary, usually disposable, discarded after discharging. Battery chemistry is usually carbon, zinc, alkaline, or silver nickel, preferably to secondary batteries for emergency operation because AC power may not be available for charging. Secondary, they can be recharged, reused many times. Battery chemistries include nickel cadmium, nickel metal hydride, lithium ion, lead acid. Here's a chart that shows some of the different battery types and their power ratings, just some interesting information about them. Okay, storage batteries, large or secondary batteries used for emergency or portable power to replace power supplies operating from AC power. Usually the battery chemistry of these is lead acid or liquid electrolyte, gel electrolyte. They're rated as 12-volt batteries, but are actually 13.8 volts. Lead acid batteries can produce useful power down to about 10.5 volts. Discharging below minimum voltage will reduce the battery life. Limiting the amount of current drawn keeps the battery cool and extends its life. So, be conscious of that. Some battery types, nickel cadmiums, are designed to have low internal resistance to supply high discharge currents. So based on your application of your battery, you may be a certain type of battery that's to be right for your application. Batteries slowly lose charge when they're not in use. That's called self-discharge. You can be minimized by keeping the battery cool and dry, but avoid freezing. Expanding water can crack the case or damaging electrodes. Some alternate power sources, solar power, photovoltaic conversion of sunlight to electricity. Solar panels or cells are actually a special type of diode, silicon p-n junctions. In solar cells, photons are absorbed by electrons, giving them enough energy to travel across the p-n junction and create DC current flow. The forward voltage created, about half of a volt, is called the open circuit voltage. Wind solar power systems require substantial energy storage. When connecting a solar panel to a lithium iron phosphate battery, use a charge controller to avoid overcharging the battery. You want to make sure you use the proper controllers. You need something between your solar panel and your batteries as a solar panel charger. Solar connections are made through a series connected diode to prevent damage from discharging back through the panel during periods of low illumination, reduced voltage. Solar panels and solar cells are made of silicon p-n junctions that are exposed to sunlight and arranged in a series parallel configuration. In what configuration are the individual cells in a solar panel connected together? They're connected in a series parallel combination. What is the approximate open circuit voltage from a fully illuminated silicon photovoltaic cell? It's 0.5 volts. Why should a series diode be connected between a solar panel and a storage panel that is being charged by the panel? To prevent discharge of the battery through the panel during times of low or no illumination. What precautions should be taken when connecting a solar panel to a lithium iron phosphate battery? The solar panel must have a charge controller. Again, you got to have something in between your solar panel and your battery. What is the minimum allowable discharge voltage for maximum life of a standard 12-volt lead acid battery? And that's 10.5 volts. If you get below 10.5 volts, your battery's not going to produce any more power on a lead acid. What is the advantage of batteries with low internal resistance? They'll have a higher discharge current. That's the main thing. So let's talk about connectors. Here's some connector technology. Pins are contacts that extend out of the connector body, male. Sockets are hollow recess contacts. We call those the female. Keyed connectors, specially shaped bodies or inserts to prevent damage from connecting incorrectly. So usually connectors are keyed so you can't, so they can't physically connect them wrong. Plugs are connectors installed on the ends of cables. Jacks or receptacles are connectors installed on equipment. Adapters make connections between two different types of connector styles, and splitters divide signals between two connectors. Here's a picture of some common connectors used in amateur radio on the power connector side. Molex connectors, the Anderson power pole, banana jacks, binding posts, terminal strips. You can terminals that are crimped to the ends of wires. There's all kinds of different types of crimped wire terminals that can be used. Anderson power pole connectors have become the standard used by Aries. Anderson connectors are sexless by standardizing on a single style. Equipment can be easily shared and replaced, and we do use that in all of our Aries stuff here. All my stuff that I use in my home shack is all converted over to the Anderson power pole type. Makes it a lot easier to connect everything together. Note that these are crimp terminals, so you need special crimping tools to attach the wires to the lugs. Avoid using pliers. Use the right tools for the job. That's pretty important. So audio connections, they come in 1/4 inch and 1/8 inch are the most popular, and they have a contact at the end of the plug, which is called the tip, and the connector at the base is called the sleeve. The third contact, and some of them, is in the middle, and it's called the ring. Phono plug jacks, also called RCAs, are used for audio, video, and low-level RF signals and control signals. Used a lot for between your amplifier for your push-to-talk lines. Here's some pictures of some RF connectors. These are a lot of these are coaxial type connectors. Each type is especially made to carry RF signals and preserve the shielding of the coax cable. Adapters are available, to connect one style to another. These are the most common ones. For us, we use the UHF, the PL259, SO239, the N types, BNCs. Those three are probably the most common. Radio signals require special connectors to be used at RF frequencies. Connectors may have about the same impedance as the feed line, or some of the signal will be reflected by the connector. Most common connector is the UHF family. UHF here does not mean ultra high frequency. UHF connectors are typically used up to 150 megahertz and can handle legal transmit power at HF. UHF connector drawbacks do have lack of weatherproofing, inconsistent performance above 150 megahertz, limited power handling. Type N series are connectors address some of those drawbacks. They can be used up to 10 gigahertz. BNC connectors are used for low power, common in handhelds for antennas. Upper limit for low SWR operation is 4 gigahertz. SMA connectors are small threaded connectors designed for miniature coax, rated at 18 gigahertz, also used for handhelds. Those are the most common ones that you see. A lot of your HTs have SMAs, and some are male, some are female, some are reverse male. So when you're buying antennas and connectors that mate with them, you need to double check what you've got. On data connector, digital data is exchanged between radios and computer equipment. Now more than it used to in amateur radio. We have a lot more data connections on our radios. D-type connectors are used for RS-232 or COM port interfaces. The model number of a D-type connector specifies the number of circuits, and a P or S depending on pins or sockets. A DB9 connector has 9 pins. And those are typical used for the COM ports on PCs, not as much so anymore. Okay, what's a typical upper frequency for low SWR operation on a 50 ohm BNC connector? Do you remember what it was? I think it was 4 gigahertz C. Yep. Which of the following describes a type N connector? Moisture resistance up to 10 gigahertz. I think that's right. The N connector has got some environmental features that makes it good for outside use. What's an SMA connector? I know it's a small threaded connector suitable for signals up to several gigahertz. And those are real common, like I said, on HDs because they're small more than anything. Which of these types of connectors is commonly used for low frequency or DC signal connections to a transceiver? That would be the RCA phonotype. All right, we're going to talk about some basic test equipment now. Analog and digital meters. A volt ohm meter, VOM, or multimeter, is the simplest and very versatile piece of test equipment. There's 2 types, analog and digital. A voltmeter can measure voltage, current, resistance, can check continuity, check diodes, test transistors. Some of them have frequency counters on them. Some measure capacitance, inductance, and a lot of them have an interface to a PC to record the readings. Digital multimeters offer greater precision than analog meters. To find a peak or a minimum value, for example, when adjusting or tuning a circuit. Experienced hams often prefer analog meters, easier to just watch the analog meter move in a display than on a digital meter. You can watch the needle find its thing on the analog meter. It's thinking and settling down. It just depends on what you're trying to measure. Meters should affect the circuit being measured in the smallest degree possible. When measuring voltage, meters should have a high input impedance so it places a minimum load on the circuit. All right, we're going to talk about the next is the oscilloscope. Oscilloscope provides a visual display of voltage versus against time. The display is updated thousands or million times per second to give a real-time view of the signal's characteristics. Allows for the measurement of fast-changing waveforms that can't be measured by other meters. Signals are connected to the scope through horizontal and vertical channel amplifiers. Amplifier gain is variable to adjust vertical sensitivity of the scope's display. Monitoring oscilloscopes are sometimes used to monitor the transmitted signals by connecting the attenuated RF output of the transmitter to the vertical channel of the scope. This assists in adjusting key waveforms, microphone gain, and speech processing. When adjusting keying waveforms, such as a CW transmitter, the operator can see on the scope display the effects of any adjustments or conditions that might cause distortion or key clicks of the retransmitted signal. One thing about scopes, some of these new radios have an audio scope on them, and you can actually see your waveform of your voice, and those kinds of things. Those are kind of neat. Okay, impedance and resonant measurements. An antenna analyzer contains a CW signal generator, frequency counter, SWR bridge, and an impedance meter, all in one package. They connect to the antenna feed line to measure standing wave ratio without having to transmit a signal at high power. They measure feed line velocity factor, electrical length, characteristic impedance, and other parameters. They're a very handy item to have around the shack. Because they use small signals, accuracy can be affected by strong signals from nearby transmitters. So you have to be careful if there's somebody that's transmitting nearby, they can maybe affect your reading, but it doesn't happen much. But an antenna analyzer is a nice piece of equipment to have around the shack. Field strength and RF power meters. They're useful. Other useful tests that include antenna efficiency and radiation pattern. Those can be measured with the field strength meter. Field strength meters are often used for comparing relative levels of RF output during antenna and transmitter adjustments. Radiation pattern is measured by placing field strength meter in one location and rotating the antenna, or the meter can be carried to different locations to determine the radiation pattern of a fixed antenna. They're useful. That'd be a very useful piece of equipment. I have had one. I've done some antenna measurements. Antenna measurements are very difficult to do, though. Uh, so directional watt meters can be used to measure both forward and reflected power. Standing wave ratio can be calculated from forward and reflected power measurements. The SWR formula is right down there. It's the ratio of the power reflected versus powered forward. And what type of test equipment contains horizontal and vertical channel amplifiers? That would be the oscilloscope. Which of the following is an advantage of an oscilloscope versus a digital voltmeter? You can see complex waveforms on a scope. D. Which of the following is the best instrument to use when checking the keying waveform of a CW transmitter? That would be a oscilloscope. What signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal? That would be the attenuated RF output of the transmitter, right? So you attenuated, meaning you can't hook your 100-watt radio into your scope. You want to attenuate it, take a portion of it to look at. Okay, so that's what they're talking about there. Why do voltmeters have high input impedance? You don't want to load the circuits you're being measured, so it would be D. Decreases the loading on circuits being measured. What is an advantage of a digital voltmeter as compared to an analog meter? I think it has higher precision. Yep, that's C. When is an analog meter preferred to a digital meter? So I think it's when you're adjusting circuits for minimum or maximum value. If I'm tuning something, an SWR meter with an analog meter is really nice to tune. You used to call them dip meters. It's easy with an analog meter to find where that dip is, as opposed to waiting for the digital meter to settle down. So it would be D. Which of the following can be determined with a directional watt meter? Let's see. Antenna front to back ratio. That's what it sounds like. Awesome. Directional watt meter. Oh, I'm sorry, I'm thinking the field strength meter. Directional watt meter you would use to measure forward and reflected power, standing wave ratio. Which of the following must be connected to an antenna analyzer when it is being measured for SWR? The receiver, transmitter, antenna, and feed line. I think C. Yep. You don't need your transmitter connected when you're checking the antenna and feed line. What effect can strong signals from nearby transmitters have on an antenna analyzer? They can desensitize it. Receive power. Let's see. Sensei can also cause nope. Receive power that interferes with the RF SWR reading. So if I'm trying to measure something locally and Jason's living next door to me and he powers up his kilowatt amplifier, he can affect my little SWR meter. Okay. Which of the following can be measured with an antenna analyzer? Power, impedance for the coax, C. All right, our next section we're going to talk about is some of the basic modes and bandwidth, some radio building blocks, and transmitters. Okay, varying the power or amplitude of a signal to add speech or data is called amplitude modulation, or AM. The information is contained in the signal's envelope, the max values of the instantaneous power for each cycle. The process of recovering speech or music from the AM envelope is called detection. So we've got amplitude modulation, and then to generate, and detection to decode. AM signals are composed of a carrier and two sidebands. It's called upper and lower sideband. When an AM signal is modulated by a tone, the two sidebands are steady and unchanging. Upper sideband is higher in frequency than the carrier. Lower sideband is lower frequency than the carrier. An AM signal with the carrier and one sideband removed is called single sideband. Single sideband transmissions have more range than AM signals because all the single sideband's power is contained in a single sideband. The single sideband's smaller bandwidth makes it possible to fit more signals into a fixed frequency range. Modes that vary the frequency of a signal to add speech or data information are called frequency modulation. The frequency is varied in proportion to the instantaneous amplitude of the modulated signal. Phase modulation is created by varying the signal's phase angle. These signals have a constant power whether modulated or not. So AM and PM signals, again, have constant power whether they're modulated or not. The FCC defines bandwidth as the width of a frequency band outside of which the mean average power of the transmitted signal is at least 26 dB below the mean power. So what does that mean? So if I'm talking, this is my voice range here. Somewhere down here is my noise floor. Here's where my noise floor starts. So when this gets between 26 dB down from here, that's where they say that's your bandwidth, from your peak down to 26 dB on each side. That ratio there is your bandwidth, okay? The difference in frequency between the lowest and highest component of a composite signal is the signal's bandwidth. The FCC limits signal bandwidth so that many stations and types of signals can share the limited amount of spectrum space. So we're limited to about 3 kilohertz on the single sideband. That's why I show, okay. Amateur signals, so here's the different types of signal types. Their typical bandwidths: AM is 6 kilohertz, amateur TV 6 megahertz. But remember, amateur TVs can be up higher. Single sideband voice, 2 to 3 kilohertz is typical bandwidth. Digital single sideband, 3 kilohertz. CW, 100 to 300 hertz, and FM voice, 5 to 16 kilohertz. Okay. So what's a link budget? When you when you add up all the power gain and losses in a signal transmission from source to receiver, that's called the link budget. In amateur radio, this is generally the transmitted power and antenna gains from the sending station minus any system losses the receiving station experiences. Losses result from ionospheric refraction, attenuation, or a variety of other causes. Link margin is the difference between the minimum power that's level needed to receive a signal and the actual power of the level received signal, and it's usually measured in dB. So if I'm trying to talk to Jason in Texas from Huntsville, and I'm running 30 watts and he can just barely hear me, we'll say we've got a link margin of about 0. That's perfect. I crank up my amplifier to 100 dB, and he goes, wow, I can hear you this much better, 10 dB better than I got a link margin of 10 dB. So it's how much margin do I have before he can't hear me anymore, right? How much power up? So that's your link margin. And my link budget was my amplifier is this much, my antenna gain is this, I lose this much through the atmosphere. And then on Jason's side, his antenna has this much, and his amplifier is this, and he can receive it. So it's that whole link budget, and then the link margin is how much extra I have to make that communication happen. Okay, so what's the name of the process that changes the phase angle of an RF signal to convey information? Well, that's phase modulation, B. What's the name of the process that changes the instantaneous frequency of an RF wave to convey information? All right, instantaneous, that'd be frequency modulation, okay? What type of modulation varies the instantaneous power of the RF signal? And that would be amplitude modulation. Which of the following phone emissions uses the narrowest bandwidth? Single sideband is the smallest here, okay? What is a link budget? Some of the transmitted power and gains when system loss is seen by others. It's going to be C. It's the sum of the transmit power antenna gains minus the system losses as seen at the receiver. What's link margin? That'd be the difference between received power level and minimum required signal level at the input of the receiver. Nearly all radios are made up of a few fundamental types of circuits. There's a variety of ways circuits are built, but basic functions are the same. Radio circuits that performs signal generation processing functions can also be performed on a digital data by software in a radio that uses digital signal processing, referred to as a software-defined radio. Filters are used to attenuate or reduce in strength or pass signals. A lot of the modern HF transceivers you buy will have attenuators, filters, a lot of cool things, circuits in them to help you improve your receive performance. Filters are classified by their response, how they act to signals. The range of signals that are passed by a filter is called the pass band. The range of signals attenuated by the filter is called the stop band, also known as rejection. Generic filter response curves here are shown. If you look at the first example here on the left, this is a low-pass filter. It passes all these frequencies and then attenuates frequencies above. This is passing the low frequency. It's a low-pass filter. Here's a high-pass filter. It attenuates the lower frequencies and it passes the higher frequencies. So that's a low-pass, high-pass filter. The cutoff frequency is the frequency at which the output signal power is reduced to half. So if you remember from our earlier charts, 3 dB down from whatever this level is here, wherever 3 dB is, that's called the stop band or the cutoff, the beginning of the stop band, the cutoff. So it's above a low-pass filter's cutoff frequency, the attenuation generally increases with frequency. So the attenuation increases, which means it rejects the frequencies there. So the cutoff is the 3 dB point of the nominal pass band. There's a bandpass filter where you attenuate certain frequencies below a certain amount and you attenuate above a certain amount, and what's in the middle is what the band that's passed called the pass band. Also a thing called a notch, where you can have a filter come in and pass everything except a frequency, a little band that you're interested in, and that's a notch filter. Okay, that's the bandwidth of that. Let's see. Low pass filters passes all frequencies below the cutoff, little or no attenuation. It's reduced by half. We talked about high pass filters, the opposite. It passes things above a certain cutoff frequency. Bandpass filters have upper and lower cutoff frequencies and pass the signals between those two. Frequency range between upper and lower cutoff is the frequency's bandwidth. Opposite of bandpass is band stop, which is a notch filter. Even those filters pass the range of frequencies, they may attenuate signals in the pass band. That's called insertion loss. All filters are going to have some type of insertion loss. The ones I build for like a low pass filter with an LCs, they always have could be up to a dB or so of loss just going in. So you have to account for that in your system design. But in the insertion loss is the term for how much how much signal is lost in the filter itself. Outside the pass band, attenuation may vary, but maximum attenuation is the filter's ultimate rejection. Okay. Another circuit, oscillators. They usually consist of an amplifier with the feedback from the output to the input. The product of gain and feedback ratio must be greater than 1 at the frequency of oscillation. And this is the basic building block, basic premise of all the oscillators we use in our radio equipment. You got an amplifier, we feed some of it back to itself and it starts to oscillate. An oscillator consists of an amplifier that increases signal amplitude gain and feedback circuit to route some of the amplifier's output back to the input. Oscillator circuits may include a filter so that the feedback is present at only the intended frequency. The oscillator output frequency can be fixed or variable. An LC oscillator feedback circuit consists of an inductor and a capacitor in parallel or series that form a resonant circuit, often called a tank circuit because of their ability to store energy. The resonant frequency of an LC circuit, determined by its values, is the frequency of the oscillator. The output frequency of a variable frequency oscillator, VFO, can be adjusted by changing the L or C VFOs are used to tune a radio to different frequencies. Two other widely used VFO circuits are the phase lock loop, PLL, and the direct digital synthesizer, DDS. The DDS is controlled by software. It's comparably stable to crystal oscillators, used as the high stability VFO in most current transceivers. Most of them have a DDS in them these days. Mixers can change signals from one frequency to another. A mixer circuit combines signals with two frequencies, F1 and F2, and produces signals with the sum and difference frequencies at its output. And that's a term called heterodyning. Example, if I've got a frequency of 14.05 megahertz and an F2 of 3.35, I'm going to get the gain and difference of those two frequencies. So I would have a frequency of 14.053 and 14.026. A multiplier, similar to a mixer, it creates a harmonic of the input frequency. Multipliers are often used when a stable VHF or UHF signal is required that cannot be generated directly at VHF or UHF. A low frequency oscillator supplies the multiplier input, and the output is tuned to the desired harmonic of the output signal. Also used in FM transmitters, used a lot there. Modulators. A modulator adds information to a carrier signal by varying the carrier's amplitude, frequency, or phase. It can be used for AM, FM, or single sideband. Amplitude modulation. There's three types of AM signals. Full AM has both the sidebands and the carrier. The carrier is represented by the vertical line in the middle of the sidebands over here. And the sidebands contain data, can contain speech or data, and the signals have been used to modulate the carrier. Double sideband removes the carrier. Okay, carrier's gone, but has the same bandwidth and information in it that the full AM signal had in it. And then the single sideband removes one of the sidebands and the carrier, and this is the lowest bandwidth of the three, and also the lowest amount of power that you need. Double sideband can be produced by a balanced modulator, which is a special mixer where F1 is the carrier and F2 is the modulator. Single sideband is generated by removing the unwanted sideband and carrier with a filter, or by combining signals with certain phase relationships called the phasing method. So there's a filtered method and phasing method to remove the unwanted sideband. Using only one sideband uses transmitted output power more effectively. Here's a diagram of a frequency or phase modulation. You have a reactance modulator, you have an oscillator, audio input, and this will generate your double sideband output, audio input here, reactance modulator, put an oscillator in, and you get the phase modulated out. Frequency modulation, the signal frequency varies in proportion to modulating the signal's amplitude. It's called deviation. Phase modulation, the deviation varies with both amplitude and frequency of the modulated signal, produced by reactance modulator connected to a tuned RF amplifier following the oscillator. When modulation is applied, the phase of the carrier will not be changed, but the average frequency will not. So let me read that again. When modulation is applied, the phase of the carrier will be changed, but the average frequency will not change. Okay? And they sound identical on the air. If you listen to frequency modulation or phase modulation, they would sound the same. It's all about the detector. Also called IQ modulation because of the I and Q signals that create the modulated output signal. This is quadrature modulation. This is used to transmit digital signals, but different combinations of I and Q signals can create signals with any form of modulation. The RF output of the combiner consists of a pair of modulated signals that have carrier signals 90 degrees different in phase. Widely used in software-defined radios, where traditionally analog components have been replaced by programming, that is filtering, modulation, and detection. That's where you'll find quadrature modulation. Here's a figure on the right that has a block diagram of the I and Q inputs, a 90 degrees phase shift network in the middle. Quadrature simply means phase shifted by 90 degrees. Which of the following are basic components of a sine wave oscillator? Let's see. D, filter and an amplifier operating in a feedback loop. What determines the frequency of an LC oscillator? That'd be the inductance and capacitance of the tank circuit, C. Which of the following is characteristic of a direct digital synthesizer? Stable crystal. D, variable output frequency with the stability of a crystal oscillator. What term specifies a filter's attenuation inside its passband? That would be the insertion loss. A, what is the phase difference between the I and Q RF signals that software-defined radio equipment uses for modulation and demodulation? So it's 90 degrees out of phase. B, what is an advantage of using IQ modulation with software-defined SDRs? Appropriate processing, right? So it allows you to, with the right processing, you can do a bunch of different stuff if you've got the IQ signals. B, which of the following functions is determined by software in a software-defined radio? Can be all those. You can do filtering, detection, modulation, all those things digitally. What is the frequency above which a low-pass filter's output power is less than half the input power? So that's the cutoff frequency. What term specifies a filter's maximum ability to reject signals out of its band? Okay, that's the maximum would be the ultimate rejection. The bandwidth of a bandpass filter is measured between what two frequencies? It's of a bandpass filter, so you've got an upper and a lower. So be the upper and lower half power or cutoff points, A. What emission is produced by a reactance modulator connected to a transmitter RF stage? So reactance modulator is used in phase modulation. B. What's another term for mixing of two RF signals? Heterodyning. What is the stage in a VHF FM transmitter that generates a harmonic of lower frequency signal to reach the desired operating frequency? So that'd be a multiplier, right? You're taking a lower frequency to get a higher one, so you're multiplying. So that'd be multiplier. What combination of a mixer's local oscillator and RF input frequency is found in the output? Be the sum and the difference. Remember, F plus F1, F minus F1, so sum and the difference. Now we're going to talk a little about CW transmitters. Simplest transmitter consists of an oscillator, an amplifier, and a means of turning the signal on and off, or the key or keyer. A single crystal oscillator can be replaced with a variable frequency oscillator to allow the transmitter to be tuned to different frequencies. So here's your basic building block. I've got an oscillator, amplifier, and an on-off switch and an antenna. Okay. By changing the frequency of the local oscillator, the VFOs can now be shifted from band to band, creating a multi-band transmitter. So now, if I've got an oscillator, if I can change the frequency of the oscillator, in this case through some crystals or variable frequency oscillator. Now I've got something I can operate on different bands. Substituting the circuits to create a single sideband signal for the VFO creates a multi-band. Now you've got a single sideband transmitter. You've got a balanced modulator. You've got some bandpass filters, a mixer. Now I'm getting more of a radio that can do voice and CW. Voice signals from a mic are processed by speech amplifier input to the balanced mixture. This is a single sideband phone transmitter. The variable frequency oscillator is the other input to the balanced modulator. The output is a digital single is a double sideband signal. So the filter is used to remove the undesired sideband, producing a single sideband. So in your modern HF radio, when you switch between upper and lower sideband, you're switching in and out one of these filters. So you're generating the double sideband, and based on your upper or lower sideband, it's going to select which one of those you're going to transmit. So they're both produced in your radio, but you filter out the one that you're wanting to use. Distortion anywhere in the transmit chain will generate unwanted spurious signals called harmonics or mixing products or splatter. An FM transmitter looks like this picture here. I've got a microphone, a speech amplifier, reactance modulator, an oscillator, multiplier, filter, and amplifier. So the carrier and modulation are generated at relatively low frequencies in FM transmitters, and the modulated signal is then multiplied to the desired output frequency. The amount of signal deviation is also multiplied. So modulation and frequency changing are performed differently in FM transmitters. It is much more practical to generate the signal at low frequency and multiply it to reach the desired band. In an example, in a 2-meter FM transmitter, the modulated oscillator frequency is approximately 12 megahertz. And multipliers select the 12th harmonic for transmission for an output of 146.52, for example. The oscillator must be divided by 12 or a 12.21 megahertz signal. The frequency deviation is also multiplied. For example, if the 146.52 megahertz signal is to have the standard deviation of 5 megahertz, the maximum oscillator deviation would be 5 divided by 12, or 0.416 megahertz, or 416.7 hertz. Okay, because it gets multiplied along with the frequency multiplication for the FM transmission. Carson's rule provides a good approximation of FM signals bandwidth. The bandwidth is equal to 2 times the peak deviation plus the highest modulating frequency. In our example, if an FM phone signal's peak deviation is limited to 5 kilohertz and the highest modulating frequency is 3 kilohertz, then bandwidth is equal to 2 times 5 plus 3, or 16 kilohertz. Okay? So bandwidth is equal to 2 times the peak deviation plus the highest modulating frequency. Over signal quality, you can overmodulate on AM signals. An AM or single sideband signal that varies excessively in responding to the modulation signal, you'll have distorted transmitted audio. And if you speak too loudly, or mic gains too high, or audio gains too high, you can have overmodulation and distort your audio. Modulation envelope of an AM signal. Look at the signal here on the left. Very nice looking AM signal. You've got this is the audio rate. What's in here is your modulation frequency. Here's your audio frequency. And this particular one, you put in like a kilohertz tone. You got a single tone. This one looks very, very nice. If I start to overmodulate, you'll see there's times here where this stuff cuts off, and I get other spurious signals down there in the frequency spectrum. So A is a poorly modulated signal. Whoops, over there. Let's see if we get this. A is a properly modulated signal. B is an example of a cutoff. Transmitter output is turned off instead of following the modulated signal. So it sounds choppy, sounds distorted. If you have cutoff, the transmitter output is turned off instead of following the modulated signal. Flat topping occurs when the transmitter output reaches a maximum limit. It cannot increase further, even though the modulating signal is increasing. That's why it clips at the top and it stops transmitting. So it's going to sound choppy and distorted. If output signal is completely cut off between peaks, the result is called carrier cutoff. Both types of overmodulation cause interference by generating spurious signals, that is distortion products, beyond normal signal bandwidth, called splatter. An automatic level controller, ALC circuit, in the transmitter helps prevent this type of overmodulation and reduces output power during voice peaks. It's controlled by properly setting the transmitted audio or mic gain and should be adjusted to activate only on your voice peaks. There's a two-tone test is used to monitor transmitter linearity, which keeps the signal clean. It only needs to be performed occasionally to note appropriate gain settings and two-level adjustments. Two-tone comes from the use of two non-harmonically related signals for the test. Most radios display carrier frequency of a single sideband. Actual signal lies between above upper sideband or below lower sideband. So your dial frequency is not exactly where your audio starts. It's where your carrier would be. Each single sideband occupies 3 kilohertz. So you'll need to stay far away from the edge of frequency privileges to avoid illegal transmissions. So for generals, using lower sideband on 40 meters, operate with a carrier frequency of at least 3 kilohertz above the edge of the band segment. Because remember, at 40 meters, we're lower sideband, so you want to be 3 kilohertz above. So 7.178, because we're allowed to go down to 7.175. So if that's my low end and I'm on lower sideband, I want to put my dial frequency on 7.178. When sidebands extend from the carrier toward the band edge or a band segment edge, operate with the displayed carrier frequency no closer than 3 kilohertz to the edge of the band, so your signal is sure to be clean. So if I'm on 20 meters here and I'm upper sideband signal and here's the edge of the band, I want to make sure I'm less than the edge, so I'm not right up against it. Okay? I don't want to put my dial frequency on 14.350 because then my upper sideband is out of band. Here's a 40 meter example. It's a lower sideband. You want to make sure you're not. This is the 7.175 is the low end general place that we can't go below that. So you want to make sure you're set up above that, at least 3 kilohertz up above. So another circuit, speech processing. The average power of an AM or single sideband signal is much lower than CW. When transmitted over HF, an AM signal in the presence of noise, interference, etc., the received signal can be difficult to understand. Speech processing increases the average power of the signal without distorting it, which results in improved intelligibility of the received signal in poor conditions. So a lot of the modern radios have speech processing. You can turn it on or off, and it works pretty good, but you have to make sure you got it all set up right and adjusted correctly. Speech processors can also amplify low-level background noise, reducing intelligibility. So careful of that. CEW key clicks. Sharp transient clicking sounds heard on adjacent frequencies as a transmitter turns on and off too rapidly during CEW transmissions, or if transmitter turns on and off erratically. Those are called key clicks. CW waveforms can be inspected using a monitor and oscilloscope, and you can see what the key clicks would look like. Just show one without it, but there's a way you can see if you've got key clicks going on, and if you've got them, you got to turn down your modulation a little bit. What control is typically adjusted for proper ALC setting on a single sideband? Transmit audio and microphone gain. Okay. What signal are used to conduct a two-tone test? Two audio signals that are not harmonically related. That's the key. Non-harmonically related signals. So that would be B. What type of transmitter performance does a two-tone test analyze? Linearity is usually linearity. How linear it is. A. What is the purpose of a speech processor and a transceiver? Increase the loudness, increase that, increase, it's going to be A, increase the loudness of your transmitted voice signal to the other guy. How does a speech processor affect a single sideband phone signal? Increases average power, not peak power, but average power. That's the difference. What is the effect of an incorrectly adjusted speech processor? All those, yeah, distorted speech, excess intermodulation. A lot of people have problems with these digital modes. not adjusting their ALC in some of these circuits, and you can really see it on a digital mode. Can cause problems if you overdrive it. What frequency range is occupied by a 3 kilohertz lower sideband signal when the carrier displayed is 7.178? It's going to be 7.175, right? It's 3 kilohertz below because it's a lower sideband. Let's see, it tells us how to do it here. We subtract 3 kilohertz from that, and we get 7.175. All right. What frequency range is occupied by a 3 kilohertz signal displayed with the upper sideband signal now? So we're going to add. So 3.34 would be B, 3.347 to 3.35 because we're adding 3 kilohertz to it. And how close to the lower edge of a band's phone segment should your display carrier frequency be with 3 kilohertz wide lower sideband? Okay, at least 3 kilohertz. If you're on lower sideband, I mean, you need to be above. At least 3 kilohertz above. A. You're not at 1 kilohertz, it's at least 3. So the ones are out, so it's got to be above. It's lower, so you got to be above. And the same thing, if you're on using lower upper sideband, you need to be below 3 kilohertz below, which would be B. And which of the following describes a linear amplifier? Our amplifier use connection frequency multiplier and B. Yep. Amplifier preserves the output, and from which the output preserves the input waveform. That's right. You're just taking what the amplifier takes, what it's given, and transmits it. It preserves it. That's what they're talking about. What circuit is used to select one of the sidebands from a balanced modulator? You have an upper sideband filter, lower sideband filter. What output is produced by a balanced modulator? So a balanced modulator produces a double sideband modulated D. Which of the following is an effect of overmodulation? Insufficient audio, excessive bandwidth, be excessive bandwidth. What is meant by the term flat topping when referring to an amplitude modulated phone signal? Properly adjusted. So it's going to be C. Signal distortion caused by excessive drive or speech level. What is the modulation envelope of an AM signal? Bandwidth of the modulation envelope, it would have to be A. Waveform created by connecting the peak values of the modulated signal. So, what is the total bandwidth of an FM phone transmission having 5 kilohertz deviation and 3 kilohertz modulation frequency? So remember how to do this? It's 2 times that, which would be 2 times 5 plus 3 is 16. What is the frequency deviation for a 12.21 megahertz reactance modulated oscillator and 5 kilohertz deviation? It's so you're going to divide. You're going to get about. You got to divide by 12. So you're going to get 416.7 hertz B. Okay, we're going to talk about amplifiers. Radio operators, HF, sometimes use amplifiers to boost their signals when conditions are poor to accommodate difficult propagation paths. On HF, high power amplifiers often use vacuum tube circuits that require operator adjustment. The efficiency of an amplifier is defined as the RF output power divided by the DC input power, also called linears. A Class A amplifier, the most linear, lowest cost signal distortion, at least efficient, because Class A's pass the entire sinusoidal input signal. They conduct 100% of the time. So Class A, good amplifier, but least efficient. Class B is known as a push-pull amplifier, and it's a pair of amplifying devices, each active during complementary halves of the signal's cycle. They have good linearity, good efficiency. Class AB, midway between the A and B. Linearity is not as good, but efficiency is better. And Class C has the highest efficiency, but it's only suitable for CEW and FM due to poor linearity. High efficiency, poor linearity. Some linear amplifiers can be operated in either class AB for single sideband operation or class C for CW. Transceivers often include a delay in the keying circuit timing so that the changeover relay is completely switched before transceiver is allowed to supply any RF current. This prevents hot switching in which amplifier is already supplying RF. It can destroy the relay or other external devices. Very important. You want to make sure you're switching between transmit and receiver. Your amplifier is connected before you start you connect before you start transmitting. Tuning and driving vacuum tube amplifiers. So if you've got a vacuum tube amplifier, you want to set the band switch to your desired frequency. You want to apply the drive power to the amplifier while adjusting the tune control to obtain minimum plate current. Find you got to dip it. Got to dip your plate current. Adjust the load then to get the peak power output, and continue adjusting until the max power is obtained. Avoid exceeding the max plate current. The input power to the amplifier may also be adjusted during the process. Tubes can be destroyed by applying too much drive. Modern amplifiers have protective circuits. Similar cautions apply to solid-state amplifiers with power transistors that can be destroyed with excessive drive power. You've got to be careful. The controls are pretty good these days, protecting them. Some amplifiers generate automatic level control signals that can be connected back to the transmitter to limit excess drive. Check both the amplifier and the transceiver manuals to be sure that they're compatible signals, so you know how to use the ALC meter reading. So that's important. It's pretty standard, but you need it. Sometimes there's a nuance there. You got to go check that out. So neutralization. HF amplifiers can self-oscillate because of positive feedback in an amplifier tube. Self-oscillation creates spurs, outputs. You may damage the tube or even the amplifier components. So the technique to prevent this is called neutralization, and it's done by creating a negative feedback, sometimes a small capacitor between the amplifier output and the input circuits. And that's usually built into your amplifier, that they've taken care of that. But if you're building your own, that's an important circuit you need to have in there. Okay. What's the effective or plate current of the correct setting of a vacuum tube RF power amplifier's tune control? What's the effect of the plate current? Produce to find that dip when you're doing it. What's a reason to use ALC with an RF amplifier? To prevent excessive drive. C. What is the current adjustment for the load, or what's the correct adjustment for the load or coupling control of a vacuum tube power amplifier? Minimum SWR, minimum plate current exceeding, okay, B. I think it'll be D, desired power output without exceeding the maximum allowable plate current. So you're trying to get those adjustments. The load and coupling controls, you're trying to balance those two to arrive at that. What is the purpose of delaying RF output after activating a transmitter's keying line to the external amplifier? To allow time for the amplifier to switch the antenna between the transceiver and amplifier. So C. What's the purpose of a neutralizing an amplifier? To limit modulation index, to cut off, to eliminate self-oscillations. B. Which of these classes of amplifiers has the highest efficiency? That would be the C class, used for FM and Morse code, CW. In a Class A amplifier, what percentage of the time does the amplifying device conduct? Class A, it's 100%, and BA. How is the efficiency of an RF amplifier determined? The DC RF output power by the DC input. B, that's correct. For which of the following modes is a Class C power stage appropriate for amplifying a modulated signal? Following modes is a Class C. FM only. It's not linear, so a single sideband or an AM, you'd have distortion on those. So FM. All right, our next section, we're going to be talking about receivers and HF station installation. Talk a little about super heterodyne receivers. Most receivers used by today's amateurs are super heterodyne. The received signals are incredibly weak and on the order of nano or picowatts. The received signals are first strengthened by an RF amplifier, then applied to the RF input of a mixer. The local oscillator is adjusted so that the desired frequency creates a mixing product at the intermediate frequency. A detector or demodulator stage follows the IF to recover the modulating information. An input amplifier gain, demodulator stage, bandwidth, and input amplifier noise can all affect receiver sensitivity. So the receiver sensitivity, I'm going to repeat that, can be impacted by the amplifier gain, demodulator stage, bandwidth, and the input amplifier noise. All those together and how you've got those set up can affect your receiver sensitivity. Super heterodyne receiver converts signals to audio in 2 steps. The front end, right here, converts the frequency of the signal to an intermediate frequency, where most of the gain of the receiver is provided. A second mixer is provided. The product detector converts the signal to an audio frequency. So you come in here on the front end, IF filter, and another IF amplifier, product detector, audio comes out here, and an audio amp stage. So you've got 2 oscillators of what's called a beat local oscillator and a BFO. So it's a 2-stage conversion, super heterodyne. Once amplified to a more usable level, single sideband and CW signals are demodulated by a product detector. It's a special type of mixer. If an AM signal is being received, a product detector or envelope detector recovers the modulating signal. Output of the detector is an audio signal amplified by the audio frequency amplifier and input to a speaker, headphones, or sound card. The RF amplifier and mixer are the receivers at RF amplifier and mixer are the receiver's front end. It processes weak signals at the original frequencies. A preselector is often used to reject out-of-band signals. A preamplifier, or preamp we call it, is used if additional sensitivity is needed, such as weak signals. The simplest possible superhet consists of a mixer connected to the antenna, an oscillator to act as the local oscillator, and a detector that operates directly on the resulting IF signal. The single frequency IF stage makes it much easier to create high quality filters and high gain amplifiers without having to be tuned. Only the LO needs to be tuned in the super het receiver. Recall the formula for intermodulation. Mixing of signals, you get F1 plus F2. For example, to convert an RF signal on 145.25 megahertz to an IF of 455, the LO must be tuned to either 4.25 minus 455, which is equal to 13.795, or to 14.25 plus 455, which is equal to 14.705. Super heterodynes have some weaknesses like all radio designs. Because they are mixing products at both the sum and difference frequencies, undesired signals can create their own mixing products at the IF. So we've got the RF input, local oscillator. We get the sum and the differences of these two. Another flaw is caused by the local oscillator and other oscillator circuits. Leakage of signals into the signal path can cause steady state signals to appear called birdies. A single figure, the next figure shows a single conversion with only one mixer converting the signal from the IF to the RF. This is the single conversion right here. RF input, one oscillator, down, single conversion. The IF stage provides most of the gain and selectivity. Filtering is applied at each IF, allows filter bandwidth selection for the desired signal. This gives the best received signal quality with the lowest unwanted noise and interference, maximizing the signal to noise ratio. In a mixer with an RF input or input frequency F1 and local oscillator F2, remember there are mixing products at F1 plus or minus F2, meaning the sum and the difference of the two. With an LO of 13.8 megahertz, a mixing product of 455 kilohertz, 0.455 can be generated by a signal of either 14.255 or 13.345. Assuming that the intended signal is 14.255 megahertz, an image response is an image response. Similar to AM single sideband and CW superhits, the linear IF amplifier is replaced by a limiter. Limiter amplifies the received signal until all amplified modulated information noise is removed, and only a square wave of the varying frequency remains. Audio information is recovered by a discriminator or quadrature detector that replaces the product detector. Once the FM signal is converted to the IF, high gain amplifiers called limiters change the signal to a square wave that only varies in frequency, not amplitude. A discriminator converts the frequency variations to audio. So here's a block diagram of an FM signal, amplifier, mixer, IF filter, limiter, discriminator, and then the audio amplifier itself. For digital signal processing, the general term, which is a general term for converting signals from analog to digital. A DSP system uses an analog to digital converter to change the signal to a digital data. A special type of microprocessor then performs the mathematical operations on the data to accomplish filtering, noise reduction, and other functions. A digital to analog converter changes the process data back to analog form for an audio to output as audio. Digital signal processing has two advantages over analog circuitry: performance, flexibility. DSP offers selectable programmable filters and allow the operator to adjust the filter bandwidth and shape and even to define new filters. Expensive functions and analog circuits can be implemented in DSP as a program without additional hardware. Just a lot of the modern receivers today and radios we buy have DSP circuits in them, and they've come a long way and they work very well. To manage the receiver gain or RF gain, when looking for weak signals, set RF gain to its maximum for highest receiver sensitivity, lower RF gain volume to reduce background noise. Automatic gain control AGC circuits vary gain of the RF and IF amplifiers so output volume stays constant for both weak and strong signals. AGC circuits changes the voltage that controls the IF gain amp. This voltage is read by the S meter, which measures signal strength. S meters are calibrated in S units. So one S unit equals up to 6 dB. Fourfold is equal to 4x change in signal strength. S9, a strong signal, is located at the midpoint of the display. Large values to the right, 20, 40, and 60, these correspond to dB above S9. Readings of S9 plus 20 dB is a signal 20 dB or 100 times stronger than an S9 signal. Receiver linearity. If the received signal is distorted, spurious signals will appear just as if transmitting stations were emitting them. The most common form of receiver nonlinearity is overload, also called front-end overload or gain compression. The solution to overload is to filter out the offending signal or reduce receiver gain with an attenuator circuit. Proper use of attenuator and RF gain controls can dramatically reduce received noise distortion caused by strong signals. So again, a lot of our modern amplifiers have some pretty good controls for these kinds of things. And if you learn how to use them, and it can really help improve your receiver reception. So, get out your manual, look at those controls. A lot of folks, we buy these radios, have all these cool features, and we only use a few of them. But if you look at your manual, there's some really cool things that will allow you to really fine tune and get your receiver working great. IF filters narrow the receiver's passband. They get rid of the unwanted signals. Notch filters remove signals in a very narrow bandwidth of frequency, such as signal tone from an interfering carrier. A lot of these radios, the newer ones, the notch filters are great. They're usually some kind of a digital form now, and they work well. So get your manual out, figure out how to use this stuff. There's really neat things in these. On the passband or IF shift, adjust receiver's passband above and below the displayed carrier frequency. So if you've got some noise if you're on a single sideband and you have some crash over here noise, you can sometimes take that, just move it a little bit and get that out of your way. And also it keeps you from interfering with the other folks. Reverse sideband controls allow switching between received CW signals above carrier frequency, LSB, and below USB and LSB. This avoids interference by placing the signals on the other side of the carrier where filtering rejects them. So that's another technique you can use. Some other ways to reduce noise. Noise blankers. They can sense sharp pulses in the IF signal and reduce the gain of the IF and audio amplifiers during the pulse. It's called blanking. Adjust your noise blankers can be set to blank the receive at different noise levels. So you have to play around with that. They do work. If you have some periodic noise that's going on, you can cut that in. It works pretty good. Noise reduction is performed by the digital signal processors. They can remove hiss and noise from the audio that is not part of the desired speech, CW. Increasing the noise reduction level may cause some of the desired signal to be removed, causing distortion. So use the least amount you needed to minimize your still intelligibly hear what you're trying to hear. So there's a trade-off there, but they do work fairly well too. And the DSP noise reducers have been around for a while, and they work pretty well. Okay, what's the purpose of the notch filter found in many HF transceivers? To reduce interference, carriers in the passband. I think that's what it is. B. What is an advantage of selecting the opposite or reverse sideband when receiving CW? I think C. May be possible to reduce and eliminate interference from the other signals. Yep. How does a noise blanker work? Increases bandwidth? Nope. Redirects noise point? Nope. Reduces gain during a noise pulse? C. It's actually reducing the gain during the noise pulses. What happens as the receiver's noise reduction level is increased? Received signals may become distorted. I think that's what we just said. A. What's the purpose of using a receive attenuation, a receive attenuator? A is a good one. Well, it would have to be A. Prevent receiver overload from strong incoming signals. All right. What does an S meter measure? It measures the received signal strength. How does a signal that's reads 20 dB over S9 compared to one that reads S9 on a receiver? Assume a properly calibrated S meter. Well, if you recall, 20 dB, if you did an old math, would be 100 times. So it's 100 times more powerful. D. How much change in a signal strength is typically represented by one S unit? Okay. How much must the power output of a transmitter be raised to change the S meter reading on a distant receiver from S8 to S9? Okay, so remember we got we just talked about each S unit 6 dB. So if I go 6 dB, what's that power? How much power increase did I have? Remember, it's 3 dB is 2 times, so that's 6 dB, so probably 4 times. So we'll see if it's C. That's the right answer. How's a product detector used? It's a FM receiver to perform frequency D, using a single sideband receiver to extract the modulated signal. That's correct. Which of the following is an advantage of a digital signal processor or filter compared to an analog filter? A is good, fewer digital A. You can do a wide range of things with a DSP filter. Different shapes, different sizes, you can create things. Which parameter affects receiver sensitivity? All three of those things, the amplifier gain, the demodulator stage, and the noise figure, all those, D. Which figure input is varied or tuned to convert signals of different frequencies to an intermediate frequency? That would be the local oscillator. What is the term for interference from a signal at twice the IF frequency from a desired signal? That would be image response. Why is it good to match receiver bandwidth to the bandwidth of the operating mode? I think results in the best signal to noise, absolutely. Okay, talk about HF station installation. HF operating with longer wavelengths and higher frequencies, higher field strengths makes grounding and interference control much more important. Now that you're going to be a general and down in the HF a little more, you have to pay a little more attention to your HF station installation. The general exam focuses on three related areas: mobile installations, RF grounding, and RF interference. Mobile radios can produce output of about 100 watts. That can output 100 watts require solid power connections capable of supplying 20 amps or more. Solid state radios perform unpredictably with input voltage drops below the specified minimum power supply range. Best power connection is a direct connection to the battery with heavy gauge wire with both of the leads fused. So mobile installation connected in your car, go directly to your battery if you can. Use heavy gauge wire, fuse both the wires. Don't use a cigarette lighter or auxiliary socket. They're usually rated for just a few amps, and they're insufficient to supply the power needed for a 100-watt radio. Talks about if you have an older models like before the 1980s or so, they were usually a little more robust, but the newer ones, they've reduced the power on the cigarette lighter output. All right. Okay, mobile installations. A limitation of mobile installations is the electrically short, smaller in terms of wavelength antennas are less efficient than full-size ones, particularly on the lower frequency bands. Some tips to improve the antenna performance: use the most efficient antenna you can. Make sure your ground connections are solid. Mount the antenna where it's clear from metal surfaces. Mobile interference. Different interference sources than home stations. When you're mobile, you got the ignition noise, spark plugs firing. If you got a diesel engine car, a lot of things that can cause noise. The alternator whine, your vehicle accessories, onboard control computers, electric motors, fuel pumps, windows. Those are all sources of interference. Winches, if you have a 4x4 with a winch on the front. So just be careful of those things. Grounding and bonding, AC grounding prevents hazardous voltage from appearing on equipment, chassis, creating a shock hazard. To manage RF, bond equipment enclosures together. Bonding means to connect 2 points together to minimize voltage differences between them. During digital operation, unwanted RF currents can cause distortion, erratic operation of computer interfaces, and activate transmitters improperly and garble digital protocols. So bonding and grounding can help eliminate some of those issues. Here's an example of a typical bonding of RF components in your shack. You want to keep all the equipment at the same the same RF voltage, the same potential. So in this case here, he's got a solid copper bus short straps between each of the pieces of equipment, and then you've got a single point ground somewhere. This is a good check. This is a good setup. I have a similar setup at my station. Been working pretty well here lately, so works out pretty good. Connect all metal equipment enclosures directly together to a common RF bonding bus. Keep connections straps and wires short. You don't want them to be electrically a wavelength of something that you're using, or it'll be an antenna. So use short, heavy inductors, 14 and 12 gauge wires, or strap best if you can. If strong RF is present, use a piece of wide flashing or screen under the equipment connected to the bonding bus. Sometimes that'll work. If ground connection is resonant at an odd number of quarter wavelengths, it will generate high impedance, which enables RF voltages or enclosures and cables on those devices. So try to avoid wavelengths of what you're trying to operate on for lengths of cables. Ground loops are created by a continuous current path around a series of equipment connections. Loops acts as a single conductor, picks up voltages from magnetic fields, from transformers, etc. So, if you hear the result, this can result in a hum and a transmitted signal that interferes with control or data signals. If you see your station operating erratically, check for ground loops and those kinds of things. Ground loops can be avoided by connecting all the ground conductors to a RF bonding bus like we've shown in the picture before, just one path. Try to avoid loops if you can. Here's some causes and some solutions. For RFI, some solutions, things are like RF chokes. You can put RF chokes on wires, on lines. You can put low-pass filters on transmitters, outputs if you have to. Just go through each of these things and try to figure out what's going on. Ask your friend who's a ham. Maybe they can help too. But usually, if you get your bonding and grounding right, you're going to do pretty good. So radio frequency interference, RFI. What are some symptoms? It varies. Interference consists of on-off buzzes or humming or clicks. If you hear that when you're operating CW or FM or data. Equipment, you can have direct detection. You'll hear called RF rectification on a speaker or something. You're transmitting, but you're hearing a squawking out of a speaker in your room. That can happen. Single sideband voice similar to AM, but its voice sounds garbled or distorted. Things you can do to help prevent that is you can install some filters. You can put chokes or use a ferrite core for conductors carrying RF current to RF choke by winding it around through a ferrite core. So you can do some things by taking a cable, wire, or they have these clamp-on things that work. You sort of have to play with them based on what your RFI interference is. Ferrite beads placed on cables to prevent RF common mode from flowing on the outside of the cable or shields is another way to try to suppress RFI. Interference to audio equipment and sensor connections can be limited by using small capacitors, 100 pico to nanofarad size, across balanced connections. Which of the following might be used in reducing RF interference to audio frequency devices? Bypass capacitor. Which of the following could be a cause of interference covering a wide range of frequencies? Let's see, arcing port electrical connection. C. What sound is heard from an audio device experiencing RF interference from a single sideband phone transmitter? Steady hum. Transmitters on the air, on off. It will be just distorted speech is the big one. What sound is heard from an audio device experiencing RF interference from a CW? Again, some clicking sounds, on-off clicking sounds. A. What is What is a possible cause of high voltage that produces RF burns? Ground wire has a high impedance on that frequency. What is a possible effect of a resonant ground connection? Yep, the RF voltage can flow on top on the enclosures of the equipment itself. Which of the following would reduce RF interference caused by common mode current on an audio cable? Ferrite choke on the cable. A. How can the effects of ground loops be minimized? Bond all the equipment enclosures together. Yep. D. What could be a symptom caused by a ground loop in your station's audio connections? Hum on your station. Receives equipment draws hum. A. Which technique helps to minimize RF hotspots in an amateur station? Bonding all equipment together. C. Why must all metal enclosures of station equipment be grounded? Blown fuse. Ensures hazardous voltages don't appear on the chassis. D. Which of the following direct fuse power connection would be used for a 100-watt mobile installation? The battery using heavy gauge wire. It would be A. Directly to the battery with heavy gauge wire if you can. How should DC power for a 100-watt HF transceiver not be? Why should it not be connected to a vehicle's auxiliary power socket? Socket may be inadequate for the current draw by the transceiver. B. Which of the following most limits an HF mobile installation? I think the efficiency of the electrically short antenna. C. Which of the following may cause receive interference in a radio installed in a vehicle? Battery charging system, fuel delivery system, controller, the computers, all those things. How does a ferrite bead or core reduce common mode RF current on the shield of a coax cable? Common mode A, creating an impedance in the current's path. Which intermodulation products are closest to the original signal frequencies? It's the odd order ones, the C, yes. What produces combination? What process combines two signals in a linear circuit or connection to produce unwanted spurious outputs? Nonlinear, so that would be intermodulation. Which of the following is an odd order intermodulation product of frequencies F1 and F2? I think that's going to be odd order intermodulation would be C. F2, F1, and that minus F2. Yeah, 2 times the fundamental minus F2 gives you that one. So here's how you calculate it. The answer is, remember, the intermodulation refers to mixing products. The odd order intermodulation refers to harmonics, as odd order harmonics are closest, referring to the second harmonic of F1. The frequency of the second harmonic, 2F that. Answer C, that's correct.